So today I will be explaining ion beam machining. So the given this is the schematic diagram of an ion beam machining. This is arrangement. This whole arrangement aperture, all instruments are placed in a vacuum chamber. Starts with a cathode, okay, it's followed by an intermediate electrode, then an anode aperture, then extra anode. Then we have a electrostatic lens for concentration of beam. Okay, ionic beam, we have to concentrate not to fall on the workpiece. Okay, and the workpiece is placed on a table. So this there's a vacuum pump on the right side because this whole uh, system aperture setup is placed inside a vacuum chamber. We have to place this setup or apparatus inside a vacuum chamber because we need the ions to have the energy. If I am placing in a non-vacuum condition, the ion beam coming out from this cathode will lose energy before it falls on the workpiece. So it should be placed in the vacuum chamber. So ion beam machining, it's generally a surface finishing process. Okay, it's actually a surface finishing process, not a actual or directly used as a metal removing one. It's actually a surface finishing process. There is metal removal at a minute level or atomic level. Okay, it's not generally used as a metal removal process. It's a surface finishing process. It's a post treatment finishing method. It's ion beam machining. Ion beam machining is generally a surface finishing process in which material removal takes by sputtering of ions. Sputtering means what actually happens is this workpiece it will be suppose it is aluminum material, so there will be fully of aluminum ions. So this aluminum ions are sputtered or thrown or scattered away. That's what actually happens. The machining, finishing process is done by sputtering of the workpiece atom. It's just removing scattered all over the place. That's how the finishing process happens. It's not a thermal process. So we won't be having direct heating or large metal removal happening in this ion beam process machining because it's a surface finishing process. Okay, it's also called an etching process. Okay, it's also called an etching process. So actual material removal is not by thermal process. There is not direct heat formed or large heat affected zone or nothing like that in ion beam machining. So it is not a thermal process. This is an important point. Unlike electron beam machining and laser beam machining, the ion beam machining is not a thermal process. Okay, that's not what actually happens here. The metal removal is not by a thermal process. The minute this is a surface finishing process, or the metal removal is taking place at a microscopic level because we only have to remove very few material, not to smooth on the surface. Okay, metal removal is through the displacement of individual atom from the surface. Okay, that is explained by sputtering of ions. The atoms are removed from here. Okay, only a very small portions of the material to be removed, not to get a smooth surface. So metal removal is through displacement of atom from the surface. So the metal removal is through the displacement of atom on the surface, so it is called sputtering. Okay. So the transfer of momentum from the incident ions to atoms of surface. The beam, the electron beam, the ion beam that's coming from the cathode, of course, it should have some momentum, right? It is having a mass of the ion, and obviously it is coming with a very high velocity, so it will be having momentum, and that momentum is transferred into the atoms of the workpiece. Okay. When IBM, a stream of charged atoms or ions of an inert gases. We will be using some inert gases as an source for the charged ions, and it is accelerated in a vacuum by high energy and directed towards a solid workpiece. Beam removes atoms from the workpiece by transferring energy and momentum of the atom on the surface of object. As you can see from the figure, we'll be having cathode and intermediate electrode and anode aperture. So from here, there will be an supply of inert gas. So the cathode filament from that will be forming already inert gas supply out there. So that's what the source of the charged ions from the inert gas, such as argon, that would eventually obviously has some energy and momentum, which would cause the removal or sputtering of atoms from the surface of the object. It is also called ion milling, ion polishing, ion etching. So ion beam machining takes place in a vacuum chamber using a charged ion. Like this important point that it has this whole machining process has to be taken in a take place in a vacuum chamber using charged ions fired from an ion source towards the workpiece by means of an oscillating voltage. Okay, there will be voltage developed across the apparatus, so it's to promote the smooth flow of the ion flow towards the workpiece. Okay, fired from the ion flow. So it is a process of knocking out atoms from the workpiece surface by kinetic energy transfer from the incident ion. Right. So we know that energy is conserved. Right? Energy cannot be destroyed or it cannot be simply destroyed. So it has to be converted. Obviously, the ion coming from this cathode will be having some kinetic energy. That kinetic energy will be used to that the energy and momentum can is converted to remove the ions from the surface. Okay, so it's what I explained this point, and the same point is repeating. This process also called ion etching, ion believers, and the mechanism of metal removal in IBM differs from EBM. Right, IBM is a process based on sputtering of phenomena, but in EBM, that's not the sputtering of phenomena. We are actually removing. Well, there will be a large metal removal rate, and actually we are removing metal removal on the surface, and there is a heat affected zone, and it's a thermal machining process. So unlike EBM, IBM is simply sputtering of phenomena, and this is a surface finishing process. So the main source of the charged ion is there is a tungsten filament which acts as a cathode at the very top of the apparatus, for which electrons are isolated. Okay, the electron will be isolated with a voltage, high voltage towards the anode. So during the passage of this electron from the cathode towards anode, they interact with the argon atom in the plasma source to produce argon ion. So argon ion is the extreme source of the ion charge for machining. Here the cathode filament, as you can see from here. From here, the electrons are moved throughout the anode. So, since anode is oppositely charged, it will be attracted towards this point. In the mean part, there will be a plasma source of inert gases that cause that form the electrons or argon ions are formed eventually in the midway between the cathode and anode. The cathode from the anode will be attracted towards the electrons from the cathode or tungsten filament is attracted towards the anode, and before reaching anode, there is a plasma source containing inert gas such as argon. So when interacting with them, there will be an argon ions are formed. Okay, these argon ions are used for machining or a surface finishing process. Okay, this is what really happens. There's a high energy ion implantation. Okay, the argon ions having some energy after interacting with the electron from the tungsten filament, and that uh, ions with energy, argon ion with energy is used to sputtering of ions. So removal atom will occur when the actual energy is transferred exceeds the usual binding energy. So binding energy with which atoms hold on the nucleus. Okay, there will be some energy with which atoms hold on the nucleus. So that energy we have not to remove that ions from the surface. We have to use an energy that should exceed the binding energy. So initially it is having an energy, a binding energy. So by that energy, the atoms or electrons are held to the nucleus. So not to remove that or break that bond, you should use an energy higher than the binding energy. So removal atom should occur only when the energy we are supplying for sputtering should exceed the binding energy. Several atoms or molecule will be ejected out and bombarding ion will become implanted deep within the material. Okay, energy greater than the binding energy of like 5 to 10 electron volt are needed to affect the removal. So you should need electron up to 5 to 10 electron volt in order to break the binding energy for removing of to affect the removal of atom. Next is next is the IBM parameters. What are the parameters that So next, the IBM parameters. So the first one is ions energy. The energy of the ion is determined by the accelerating potential of the ion source electron and for the ion beam. It is moving with the potential right from cathode to anode. So it's one of the main parameters of the efficiency of the working of IBM, the ions energy. Next, the ion current. Basically, there will be a current flowing from the cathode to anode. The ion current or ion current density determine the sputtering rate, the removal rate at which the removal of ions take place. So ion current, then ion beam power, and beam power or power density defines the material sputtering rate. Then working gas, I mean the gas will be using, right, determines the optical component material sputtering yield, then the angle of incidence and optical motion pattern. These are the main parameters of IBM. Then the factors affecting the metal removal rate. Obviously, there will be metal removal rate. This is a surface finishing process. The metal has to be removed, but only at the micro level. Okay, it's not removing just like a thermal process, thermal machining process like EBM or laser machine beam machining. So here we will only need a very mild metal removal rate, but there is metal removal rate of course. So there should be factors affecting the metal removal rate. So spring yield is simply metal removal rate because it's a function of atomic number and binding energy. So more metal removal rate means you have to spend more binding energy. I mean number of electrons. Sputtering yield itself means MMR or metal removal rate. It's a function of atomic number, binding energy, grain size, the number of electron shell of the workpiece metal, and the sputtering yield. It depends on the atomic weight of the ions which is coming. Okay, normally we will be using normally as argon, so it will be argon ion. So depends on the atomic weight of it, and ions having a high atomic number will be giving higher MMR. So if we use the weight or atomic using ions of having higher atomic weight, will be getting a much higher MMR. Then the angle of incidence, the sputtering yield increases gradually, reaches a maximum at an ion incident angle of nearly 50 degrees Celsius. Okay, so it increases, initially it increases up to 50 degrees Celsius, the angle of incidence, but it decreases rapidly. So as the ion incidence angle increases, more atoms of the workpiece get knocked out. Okay, sputtered or removed. So that's about the angle of incidence. Then specific sputter machining rate increases linearly with the amount of ion energy. So it is directly proportional to the ion energy. And the machining depth increases with the current density. If you're using a very high current density, we would be getting a much higher machining depth. Okay. So up next, the factors affecting the surface finish in IBM. So what are the factors affecting surface finish? We have discussed the metal removal rate, right? But the surface finish is our main aim because this is a surface finishing process. So surface roughness increases with increase in the size of the grain structure, ion energy, and current density. We have discussed about ion energy and current density. It's directly proportional to the, I mean, method removal or the working, and it also depends on the grain structure. Okay, the different workpiece will be have. I mean, different material will be using for different workpiece, right? So obviously, its grain structure is also different. So at roughness really depends on the grain structure and density. And for an increase in angle of incidence, increases the surface roughness. Okay, so if it increases the angle of incidence, obviously it will increase the surface roughness. For a low current density energy, smaller value of surface roughness, and surface roughness increases from for 0 to 50, then decreases rapidly. We have discussed that earlier, and the surface morphology has an effect on the final surface finish. Okay, so if you're selecting some material of obviously different material will be having different surface morphology, it would affect the surface finish after IBM. Okay, so these are the main process. These are simple graphs showing the surface roughness and ion current density. As you can see, the current density and surface roughness is directly proportional. So it increases when ion current density increases, surface roughness also increases. Okay, so then you can see the with respect to beam angle. So initially it increases up to a particular angle, then decreases gradually, steep decreasing. So these are the factors affecting the surface finish. Then there won't be we won't be able to discuss the heat affected zone in IBM because this is not a thermal machining process, right? This is surface finishing process, and the effect or the heat affected zone will be only up to a very level, or only up to 1 micrometer. So there won't be much larger heat affected zone that can be seen with the naked eye because this is not a thermal machining process. It's just simply a surface finishing process where the metal removal and heat affected zone is only seen at the atomic level. Okay, you can't see it, so there won't be the effect or heat effective zone. The effect due to HAS or heat effective zone will be very much negligible, so won't be considering the heat effect as well. So this is all about the IBM working and its process. Okay.